So I know you're excited about phylogenetic trees. Here we're going to finish the PowerPoint we started on Wednesday and then start a new one today. And there's an exercise, which is what I was trying. I got another camera so that I can point to this as I'm writing. There's this paper, and maybe we'll get to this, maybe we won't. We'll see. All right. Share files. And if I forget to put the little hand on the PowerPoint, do remind me. I'm sorry I keep forgetting that. And who knows what's going on. All right, let's see. We're talking about types of trees, or I was telling you things about the branches. So if I remember right, we ended here. So a little hand, there you go. I was elaborating on what does this tree mean. And I was telling you that I ask you in exam, does this tree convey the information that mammals are more closely related to birds than to reptiles? And it's common for you to look at this and go like, yes, because the birds word here appears close to the mammals word here. So the answer is yes, but that's the wrong answer. Let's say that these branches don't have any scale, so then it doesn't really matter the length of these branches. If there's a scale somewhere and then this branch is shorter between here, your leaf, your terminal node, which is birds, and this node here, which is the ancestor, right? So, and okay, this length doesn't matter, okay? So this is just spaced out enough so that you can write stuff here or draw or whatever. The branch length that matters is this one, or this, and this. And this is just however long you need to make that space. So if there's a scale somewhere, then the length of this branch and this branch matters. If there was a scale and this one was shorter than this, then you could say that mammals are more closely related to birds than to reptiles. But if they're the same length, then the fact that they appear next to each other means nothing. So if we had swapped birds and reptiles here, then you say that the tree still has the same topology. So the topology is the relationships between these entities. So I told you, compared to a mobile, that thing that hangs above the baby's head. So, okay, this is the mobile, no, upside down, but so what you're looking is the branching pattern, right? So this tree here has the same topology as this. So even though they are presented differently, and we can even do like this and that, they have the same topology, even though they don't look the same, because they are they're demonstrating the same relationships between the entities, they are the same tree, those two trees have the same topology. So C and D are the two most closely related. Remember, you always start from like the closer, the shorter branches, the shorter distance between your leaves, and then the internal nodes, which are the ancestors to those leaves. So C and D as the two most closely related to each other, and then B resembles C and D more than A resembles C and D. And the same thing is seen here, C and D, and then B, and then A. All right, so hopefully now you know how to interpret phylogenetic tree. And so there are different, so actually I already told you about the topology. As long as they're conveying the same information, doesn't matter how you're displaying the tree, they're the same topology. Then we look at the branch length, and I told you the computer scientists call that an edge. So instead of branch, they call it edge. And there are trees that are called cladograms, Some trees are called additive, and other trees are called ultrametric. So you're going to see differences between them. And the cladogram, the branch length has no meaning. As I was telling you, if there's no scale anywhere, then you say, oh, this is a cladogram. But if there is a scale somewhere, then that is indicating that the length of that branch correlates to the genetic distances. In that case, you have an additive tree. And then I'll show you what an ultrametric peers. So if you look at these trees, and put on the chat what are some differences you see between them.